Quick check. Can everyone hear me? Just type acknowledgement in the live chat or something. I've had some problems with it the last 2 streams. Awesome. Thank you. All right, howdy. So today we're going to be talking about orthogonal subspaces. So I'd like to start by just reviewing the definition I gave last time. So suppose we have Rn, and we're given 2 subspaces x and y of Rn. Then we say that they are orthogonal if x transpose multiplied by y is equal to 0 for every x and x and every y and y. If x and y are orthogonal, we write x, and then we do this kind of line with a bar over it, is orthogonal to y. And that's how we read this symbol. It means is orthogonal. So let's start with an example. So I'm going to define 2 subspaces of R2. X in R2 is going to be defined to be the set of vectors alpha, alpha, where alpha is a real number. And my second subspace y is also going to be a subspace for R2. And it's going to be defined to be the set of vectors alpha, negative alpha, where alpha is in R2. Now, suppose we take a vector from x and a vector from y. So, for example, we take alpha, alpha from x, and just use a different letter. We take beta, negative beta, from y. Then what we can do is we can take their scalar product. So call this x, call this y. Then x transpose times y is the same thing as the matrix multiplication of the row vector alpha alpha with the column vector beta negative beta. And this is precisely alpha beta minus alpha beta, which is equal to 0. So for any 2 vectors, x and y, in the subspace big X and big Y, if we take their scalar product, we get 0. So x and y are orthogonal spaces. Hold on 1 second. And if you want to ask me questions, as usual, I'll be in the Discord voice channel. So let's do another example. So this time I'm going to look at 2 subspaces, x and y in R4. And they're going to be defined as follows. X is going to be the set of vectors 0, 1, or actually, how about this? I'm going to define it as a span. So it's going to be the span of the vectors 2, 1, 1, 0, and the vector, say, 1, 1, 0, 0. And now I'm going to define another space y. And this is going to be the span of the vectors. Well, first off, I'm going to have 1 and -2, 0, 0. And then the other vector I'm going to have is going to be 1, 0, -2, and +2. So I claim that x is orthogonal to y. So to do this, let's note that every vector in x is a linear combination of these two vectors. So I'm going to call this vector right here v1. I'm going to call this vector right here v2. I'll call this vector right here w1 and this vector right here w2. So in order to show x and y are orthogonal, what we have to check is we have to check that for all alpha 1, alpha 2, beta 1, beta 2, and these are all real numbers, that when I take alpha 1 times v1 plus alpha 2 times v2, and I take its transpose and I multiply it with beta 1 w1 plus beta 2 w2, I get 0. And in order to check this, note that this is the same thing as alpha 1 beta 1 multiplied by v1 transpose times w1 plus alpha 2 beta 1 multiplied by v2 transpose w1, and then plus plus alpha 1 beta 2 times v1 transpose times w2, and then I'll just put the other thing over here, alpha 2 times beta 2 times v2 transpose times w2 has to be equal to 0. Well, if we want to show this second equality, it suffices to show that v1 transpose times w1 is equal to 0, v1 transpose times w2 is equal to 0, and v2 transpose times w1 is equal to 0, and v2 transpose times w2 is equal to 0. Because if all four of these equalities are true, then it follows that the second line here is 0, which implies the first line is 0, which would imply that x and y are orthogonal, which is what we really want to show. So we've reduced our calculation to calculating 4 distinct scalar products. And so that's what we're going to do. So first thing we'll do is we'll look at v1 scalar product with w1. So this amounts to computing 2, 1, 1, 0 multiplied by 1, -2, 0, 0. And you can see right away that this is going to be 2 times 1 plus 1 times -2 plus 0 plus 0, and you do all this arithmetic, you just get 0. So the first relation here is true. Let's check the second relation, V1 transpose times W2. So again, I have to look at 2, 1, 1, 0. And this time I have to multiply it by 1, 0, -2, 0. And of course, this is simply 2 times 1 plus 1 times 0 plus 1 times -2 plus 0 times 0, which of course is just equal to 0. So that verifies the second relation. Now let's verify the third relation. So I have to look at V2 transpose. So in this case, 0, 0, 1, 1. And then I have to multiply it by W1, which in this case is 1, -2, 0, 0. And you can see immediately this 1 is getting multiplied by the 0, this -2 is getting multiplied by the 0, this 0 is getting multiplied by this 1, and this 0 is getting multiplied by this 1, so it's just 0. So that's easy enough. And then we have to do one more, which is we have to look at 0, 0, 1, 1, and then we have to multiply it through by 1, 0, -2, +2. Oh, which I was missing that up here, but it doesn't change anything. So here I should have 1, 0, -2, +2. And when I do this computation, I'm going to get 0 plus 0 plus 1 times -2 plus 1 times 2, which of course is just 0. And so this verifies the last two relations, which shows that this expression vanishes, which shows that any linear combination of the vectors v1 and v2, taking the scalar product with any linear combination of the vectors w1, w2 has to vanish, which implies that x is orthogonal to y. So this gives us yet another example of orthogonal subspaces. So I now want to show, or I want to give a definition first, namely the orthogonal complement. So suppose we're given any subspace y of Rn, then the set of all vectors in Rn that are orthogonal to every vector in y will be denoted by y, and then we have the little orthogonal symbol right here. And so this is called the orthogonal complement of y. And it is precisely these vectors y, such that when you take the scalar product with x, precisely the set of these vectors x, such that when you take the scalar product with y, you get 0 for every y in your subspace. Let's do a simple example real quick, and this is one I did last time as well. So suppose we look at a subset of R3. So I'm going to look at the set of, how about the set S in R3 of all x, y, z with x plus y plus z is equal to 1, or is equal to 0. Then S is a plane and the orthogonal complement of S is just the one-dimensional subspace spanned by the normal vector one, one, one. So this is a simple example, but we will do much more interesting ones later today. Before I get to that, though, I just want to kind of make a few simple remarks on the nature of orthogonal subspaces. So let's suppose that X and Y are orthogonal subspaces of Rn. The first claim we're going to make is that X intersects Y in the 0 subspace. The second claim we're going to make is that if Y is a subspace of Rn, then the orthogonal complement of Y is also a subspace of Rn. So I'm going to start by proving one. So here's how this goes. Suppose X, or actually let me use a different letter. Suppose V is an element of the intersection of X and Y. Then V transpose times V has to be equal to 0 because X and Y are orthogonal. So again, what it means for X and Y to be orthogonal is that if you take a vector from X and a vector from Y and you take their product, their scalar product has to be 0. So since V is a member of both of these spaces, we can take its scalar product and its scalar product has to vanish. But V transpose V is simply going to be the sum of the squares of the components. So I'm going to have V1 squared plus V2 squared plus blah, 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 blah. Vn squared is equal to 0. And, all of these are squares, so they can either be 0 or positive. And so this implies that Vi is equal to 0 for all I. And thus, V is equal to the 0 vector. And so that completes the proof of the first remark here. Now let's prove the second remark. So suppose that Y is a subspace of Rn, then the claim is that Y transpose is also, not Y transpose, the orthogonal complement of Y is also a subspace of Rn. So now let's do the proof of 2. So here's how this goes. Suppose V1 and V2 are elements of the orthogonal complement of Y. Then this implies that X transpose times V1 is equal to 0. X transpose times V2 is equal to 0 for all X in Y. But this, in turn, implies that X transpose times alpha 1 V1 plus alpha 2 V2 is equal to 0 for any alpha 1, alpha 2 real numbers. And this implies that y, or the orthogonal complement of y, is closed under addition and scalar multiplication. And if this is true, then the orthogonal complement of y must be a subspace. And so this completes the proof of part 2 of these remarks. And so now we can move on to some more meaty examples. To do this, I need to give you guys 2 definitions. So these will be important definitions for the rest of the chapter. Fortunately, they're mainly about notions that we've already seen in the past. So R of A is going to be the set of all vectors B, and I guess, hold on before I do anything, I should say here, A is an M by N matrix. And then associated to this M by N matrix, we have 2 different subspaces. So first, we can form the column space of A. And the column space of A is going to be a subspace of Rm. Because, this is a matrix. It's an M by N matrix. So the columns themselves have length m, and so for every column we get a different vector, and that vector lives in Rm. The other subspace of interest to us is R of A transpose, which is precisely, of course, the column space of A transpose, which, of course, is simply a subspace of Rn. Because when you flip A, it becomes an n by m matrix, and so the columns have length n, and thus with an Rn. So these are 2 very interesting subspaces. And what we're going to be interested in is kind of conceiving of them and their relationship to orthogonal subspaces. So here is our first observation. R of A transpose is going to be orthogonal to the null space of A. So here's our first claim. And so let's try to understand why this is true. Suppose V is a vector in the null space of A. Then V multiplied with R is equal to 0. Actually, let me write it like this. Then V multiplied with R is equal to 0 for any row of the matrix A or C transpose times V is equal to 0 for any column of the matrix A transpose. So to understand why this statement is equivalent to this statement, think about it. The rows of A correspond to the columns of A transpose. So if the rows times the vector v are equal to 0, that means the transpose of the columns times the vectors v has to be equal to 0, which implies that the null space of A, or it implies that the null space of A is orthogonal to the row space of A transpose, or I'm sorry, the column space of A transpose. And the only thing I'm really not spelling out precisely is that because this is true for any column of the matrix A transpose, it is also true for any linear combination of columns. Okay. Now, let's look at a somewhat more sophisticated result relating these different spaces. This is called the fundamental subspaces theorem. If A is an m by n matrix, then the null space of A is the orthogonal complement of R of A transpose, and the null space of A transpose is equal to the orthogonal complement of RA. We only have to prove one of these, and the other will follow. So the one I'm going to focus on is this. So here's how we're going to prove this. We've already established that the null space of A is orthogonal to R of A transpose. Now, what we need to show is that if V is an element of R of A transpose, or the orthogonal complement of it, then V is an element of the null space of A. Because if we prove this, then this equality will follow. So here's how we can see this. If V is an element of the orthogonal complement of R of A transpose, then V times alpha 1 C1 plus alpha M Cm transpose is equal to 0, where C1 through Cm are the columns of A. Consequently, because this is true for any choice of alpha, we have C1 transpose times V is equal to 0. C2 transpose times V is equal to 0. And then blah, 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 Cm transpose times V is equal to 0. And these imply that V multiplied by the following matrix. So the first row is going to be C1 transpose, the second row is going to be C2 transpose, etc. is equal to 0, 0, dot, 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 0, 0. But this right here is the first column of, this is the column of A transpose. So this is the first column of A transpose. This is the second column of A transpose. This is the mth column of A transpose. So this matrix right here is in fact simply the matrix A. This implies that A times V is equal to 0, which implies that V lies in the null space of A. So that shows that every vector in this space actually lies in this space. And the other direction of it follows from what I proved before. So, in order to get the second result here, all you do is you take the first result and you replace A by A transpose, and you note the fact that A transpose transpose is just equal to A. So that completes the proof of the fundamental subspaces theorem. We have another result that I want to talk about. And this is the first kind of major structural result on the structure of orthogonal subspaces. So suppose that S is a subspace of Rn, then the dimension of S plus the dimension of the orthogonal complement is equal to n. Furthermore, if x1 through xr is a basis for S, and xr plus 1 through xn is a basis for S transpose, then the union of these two things, the list that starts with these and then ends with these, is also a basis for Rn. So here's how the proof goes. We're going to start with the first statement. So let x1 through xr be a basis for S, and set A to be the R by N matrix x1 transpose, x2 transpose, blah, 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 xr transpose. So I'm taking the first vector of my basis and I'm making it the first row of my matrix. Second vector of my basis becomes the second row of my matrix, etc., etc. This gives me A. Then the orthogonal complement of this is precisely the same thing as the orthogonal complement of S, but by the fundamental subspaces theorem, it's also the same thing as the null space of A. And by rank nullity, so this is a theorem from chapter 3, we have that the dimension of NA is equal to N minus R, where R here is the dimension of S. So this implies, in particular, that the dimension of the orthogonal complement of S plus the dimension of S is equal to N. And that completes the first part of the proof of theorem 5.22. Now let's concern ourselves with the second part. So we're going to suppose that x1 through xr is a basis for S, and xr plus 1 through xn is a basis for the orthogonal complement of S. Then we want to show that the union of these two bases forms a basis for Rn. So here's what we're going to do. Suppose x is a vector. Actually, I'll use a different letter. Suppose v is a vector in Rn. Then what we can do is we can note that v times x1 is equal to, or I'm sorry, how would I write it like this? V transpose times x1 is equal to alpha 1 for some alpha, and then v transpose times x2 is equal to alpha 2 for some alpha 2, blah, blah, blah. V transpose times x n is equal to alpha n for some alpha n. Now consider v minus alpha 1 hold on one second, let me think about this. Actually, I'm going to do this slightly differently. So what I'm going to do is I am going to make the following observation. Let's consider a linear combination of all of these vectors. So suppose we look at alpha 1 times x1 plus alpha 2 times x2 plus blah, 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 alpha r times xr plus alpha r plus 1, xr plus 1, blah, 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 alpha n xn. And suppose we set it equal to 0. So now the alpha i's are just arbitrary real numbers. We can rearrange this equality to see that alpha 1 x1 plus blah, 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 alpha r xr is equal to negative alpha r plus 1 xr plus 1 minus blah, 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 minus alpha n xn. And so let's call this vector here w, and let's call this vector here say v. And so this implies that v is equal to w, or w is equal to v. But now note that w is an element of S, and v is an element of the orthogonal complement of S. And in particular, we know that S is orthogonal to its orthogonal complement, which implies that their intersection is just the zero vector. So if w is in S and v is in the orthogonal complement of S, and these two things are equal, it follows that w has to be equal to v has to be equal to 0. But this implies that x1 through xn is linearly independent. And if it's linearly independent, and it's a set with n elements, it has to be a basis by our theorems on bases. So this completes the proof of theorem 5.22. Now here is our next main result. But, well, to do it I have to give a definition first. So I have to define the notion of a direct sum. So the direct sum is a construction that takes two vector spaces, u and v, and produces a third vector space. Here's how it goes. Both u and v are subspaces of a subspace w. Then we can write, under the following assumption. If every w, little w and big W can be written uniquely as a sum of u plus v, where u is in big U and v is in big V, then we say that w is a direct sum of u and v, and we write w is equal to u and then a plus with a circle around it, v. So this is the notion of a direct sum. So let me try to kind of give some examples. So here's a very simple one. Suppose we look at R3. Well, I'm going to look at two different subspaces of R3. One subspace is going to be the span of the vectors. So I'm going to take the standard basis vector e1 and e2. And the other subspace is going to be defined to be the span of the standard basis vector e3. Now, every vector v in R3 can be written uniquely as alpha 1 times e1 plus alpha 2 times e2 plus alpha 3 times e3. And here I'm just implicitly using the fact that e1, e2, e3 form a basis. And so when you have a basis, every vector can be written uniquely in terms of that basis. But now we can understand our basis as having two parts. First off, we have alpha 1 e1 plus alpha 2 e2. And then we also have alpha 3 times e3. So this right here is a vector v, and this right here is a vector u. And so every vector v can be written uniquely as a sum of u, I'm sorry, let me go back here, take a different letter. I'm going to call this x actually, and then I'll call this x just to be consistent with the lettering in the definition. So every vector x can be written uniquely as the sum of u and v, where u is in the span of E1 and E2, and v is in the span of E3. And so that shows that R3 here is the direct sum of the span of E1, E2 with the span of E3. Let's do one more example. So suppose we look at actually, I'm going to hold off for a little bit. I'll give more examples in time, but let me just kind of focus on the essential point of it. The idea is that when you have these two subspaces, u and v, you can take your arbitrary vector in your total space, w, and you can break it down uniquely as a direct sum. One part coming from u, one part coming from v. And this gives us kind of a way to sometimes understand our whole subspace w as an amalgamation of the subspaces u and v, and that's what we use this direct sum language to kind of denote. So here's the key result that we want to prove using it. So this is the theorem. And the theorem is that if S is a subspace of Rn, then Rn is equal to the direct sum of S with its orthogonal complement. And this is actually kind of a result that follows immediately from the previous theorem. To see why, what we do is we suppose x1 through xr is a basis for S. Then, actually, before I do that, I'm going to assume and xr plus 1 through xn is a basis for the orthogonal complement. Then our previous theorem tells us x1 through xn forms a basis for Rn. Consequently, every vector v, or how about this, every vector Yeah, I'll stick with V. Or maybe Y. Every vector Y in Rn can be written uniquely as a linear combination of these n vectors. So we can write y is equal to alpha 1 times x1 plus alpha 2 times x2 plus blah, 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 alpha n times xn. And then here I'm just using the fundamental property that x1 through xn forms a basis. But this tells us something. So to see what it tells us, let's take it to another page. And let's note that we can understand this big sum as having two subsums. So one sum is the sum of alpha 1 x1 plus blah, 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 alpha r xr, and then plus alpha r plus 1 xr plus 1 plus blah, 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 alpha n xn. And here, this gives us an element u. This gives us an element v. And u and v, or I should say u lies in S, v lies in the orthogonal complement of S, and u, v are uniquely determined. Consequently, it follows that Rn has to be equal to the direct sum of S with the orthogonal complement of S. And this completes the proof of this theorem. So this is one way that you can find direct sum decompositions. You simply take a space S, you form its orthogonal complement, and then you can write every vector in the ambient space uniquely as a vector in terms of a vector in S and a vector in the orthogonal complement of S. So now we have one more theoretical result. So here's the thing. If S is a subspace of Rn, then the orthogonal complement of S, well, the orthogonal complement of the orthogonal complement of S is equal to S. So here's how the proof of this goes. So first, note that if V is in S, then V transpose times W is equal to 0 for all W in the orthogonal complement of S, which implies that V is an element of the orthogonal complement of the orthogonal complement of S. Thus, S is a subspace of the orthogonal complement of the orthogonal complement of S. Now, here's what we can note. The dimension of S plus the dimension of the orthogonal complement of S is equal to n. and the dimension of the orthogonal complement of S plus the dimension of the orthogonal complement of the orthogonal complement of S is also equal to n. So I can subtract this equality from this equality, and it implies that the dimension of S is equal to the dimension of the orthogonal complement of the orthogonal complement of S. So, any basis for S must be a basis for the orthogonal complement of the orthogonal complement, and thus S is actually equal to the orthogonal complement of the orthogonal complement. All right. So this is kind of an idempotent relation, which is to say, if you start with the space S and you take its orthogonal complement, you'll get a new space. But if you take the orthogonal complement again, you'll get the original space back. So the proof was relatively straightforward. And now we're on towards our last theoretical result. So let's suppose that A is an m by n matrix, and B is a vector in Rm. Then either there's a vector x in Rn such that Ax equals B, or there's a vector y in Rm such that A transpose times y is equal to 0, and y transpose times B is equal to 0. So let's try to understand why this is true. Suppose Ax equals B has no solutions. Then what we can do is we can note that Rm may be regarded as the direct sum of the null space of A transpose plus, or direct sum, the column space of Ra transpose. And to obtain this direct sum relation, I'm simply using a fact that we observed earlier, which is, I believe, all the way up here, that n of A transpose is equal to R of A transpose. So let me make sure I'm okay with this. Oh, wait. I'm not. Sorry, I should get rid of this right here. Now I have the right relation. So I've expressed Rm as a direct sum using my earlier results. So what we're doing is we're assuming that Ax equals B has no solutions. So B does not lie in the column space of A, which means we can write B uniquely as two things, or as the sum of two things, U plus V, where U is an element of the null space of A transpose, and V is an element of the column space of A, and consequently, it follows that because B does not lie in the column space, V here has to be equal to 0, and U here, actually, hold on, I'm slightly mistaken. No. I can go back. I can write B as U plus V here. Now, note that U is in the null space of A transpose, which implies that U times A transpose is equal to 0. But it also implies that U transpose times B is going to be equal to U transpose times U plus U transpose times V, but because V is in the column space of A and U is in the null space of A transpose, we have U transpose V is equal to 0. So this is just equal to U transpose times U, and this cannot be 0. As otherwise, U would have to be equal to 0, and B would lie in the column space. So, this shows that there exists a vector y, in this case I'm calling it u, such that A transpose times y is equal to 0, yet when I multiply, or I take the scalar product of y and b, I get something non-zero. And it all just fundamentally relies on this direct sum decomposition. So this is the last of our main theoretical results, so let's do some actual computations. So here will be our first example. So I'm going to let A be this matrix. And what I want to do is I want to find bases for the null space of A, the column space of A transpose, the null space of A transpose, and the row space, the column space of A. So here's the first observation we can make. Row operations on A preserve the null space of A and the column space of A transpose. So we may use Gauss, the Gauss-Jordan algorithm to find our bases for these two spaces. So this is going to be the strategy we employ. So the first thing I'm going to do is I'm going to transcribe our matrix. We have 1, 1, 2, 0, 1, 1, 1, 3, 4. And right now I'm going to try to find a basis for the null space of A and the column space of A transpose. And so I'm going to do that by applying row operations to this matrix to make this matrix as simple as possible. So the first thing I'm going to do is I'm going to set row 3 here to be equal to row 3 minus row 1. And I get 1, 1, 2, 0, 1, 1, and then 0, 2, 2. The next thing I'll do is I'll set row 3 to be equal to row 3 minus 2, row 2. This gives me 1, 1, 2, 0, 1, 1, 0, 0. Next thing I'm going to do is I'm going to set row 1 to be equal to row 1 minus row 2. If I do that, I'm going to get the matrix 1, 0, 1, 0, 1, 1, 0, 0, 0, and this is now in row reduced echelon form. And so I can look at this matrix and I can identify this one right here and this one right here as corresponding to bound variables. And this whole column right here corresponds to a free variable. And we'll call that free variable x3, and we'll call the two bound variables x1 and x2. So to translate this into the language of linear systems, we have to have x1 plus x3 is equal to 0. Because basically what I'm going to do is I'm going to take this matrix right here, 1, 0, 1, 0, 1, 1, 0, 0, 0, multiply it by x1, x2, x3 to get 0, 0, 0. And it would imply that x1 plus x3 is equal to 0, x2 plus x3 is equal to 0. So since I have a free variable x3, why don't I just take x3 here to be equal to 1? And this implies that x1 is equal to -1, x2 is equal to negative 1, and thus the x vector is the vector -1, -1, 1. And so this right here will form a basis for the null space. So we have the null space of A is equal to the span of the vector -1, -1, 1, and the basis is just equal to -1, -1, 1. The next thing we're going to do is we are going to compute A basis for the row space, or the column space of A transpose. So the column space of A transpose is spanned by the transposes of the two rows that we found in the two non-zero rows that we found in the row reduced echelon form. So the first row is 1, 0, 1. So it's the span of 1, 0, 1. And the second row, which was 0, 1, 1. And the basis, of course, is just simply these two vectors. All right. So now we have found the basis for the null space of A and the column space of A transpose. It remains to do the same thing for the null space of A transpose and the column space of A, but it's basically an analogous computation, because all we're going to do is we're going to take A here and replace it by its transpose and go through the exact same set of calculations. So here's how we do that. We note here that A transpose is equal to 1, 1, 2, 0, 1, 1, and 1, 3, 4. And we're going to apply row operations to make this as simple as possible. And row operations will preserve the null space of this, as well as the column space of A itself. So the first thing I'm going to do is I'm going to set row 2 to be equal to row 2 minus row 1. I'm going to set row 3 to be equal to row 3 minus 2 times row 1. And this is going to give me the matrix 1, 0, 1, and then 0, 1, 2, and then 0, 1, 2. Next thing I'm going to do is I'm going to set row 2 here to be equal to, row 3 here to be equal to row 3 minus row 2, in which case I'm going to get the matrix 1, 0, 1, 0, 1, 2, 0, 0, and this is now in row reduced echelon form. So now I can go about considering the subspace, or the null space. I note that this right here is a bound variable, corresponds to a bound variable x1. This corresponds to a bound variable x2. And this corresponds to a free variable x3. So to write it down, I have to consider the equation 1, 0, 1, 0, 1, 2, 0, 0, 0 times the vector x1, x2, x3 being set equal to 0, 0, 0, which is the same thing as the linear system x1 plus x3 is equal to 0, and x2 plus 2x3 is equal to 0. So, since x3 is a free variable, I may as well simply set x3 is equal to 1. This implies that x1 is equal to -1, and x2 is equal to -2. So, consequently, I obtain the vector x equals -1, -2, +1. And this gives us a basis for the null space of A transpose. So the null space of A transpose can be regarded as the span of the vector -1, -2, and 1, and it has as a basis simply the vector -1, -2, and +1. Now, the final thing I need to do is I need to look at the column space of A. Well, again, this row reduced echelon form tells us what the column space should be immediately. Because all I have to do is I have to look at the first row here and the second row here, which are the only two non-zero rows, and simply transcribe them. So the column space of A is going to be the span of the vectors 1, 0, 1 and 0, 1, 2. And the basis here is going to be the vectors 1, 0, 1 and 0, 1, 2. And that completes the proof of our statement. Or rather, it completes the computation of these 4 subspaces. So let's see what else I want to do today. There's one last thing I want to talk about. So what we've learned above is we've learned that if A is an M by N matrix, we may interpret it as a linear map from Rn to Rm. And we've learned that Rn has the following direct sum decomposition. It can be written as the null space of A direct summed with the column space of A transpose. Now, the image of A is just the column space which is the same thing as R of A. Now, let's see what we know here. We know that A, so if the matrix A has rank R, then the dimension of the null space of A is equal to n minus R. So the rank, or sorry, not the rank, the dimension of the column space of A transpose is equal to R. But we also know that the dimension of the null space of A transpose is also equal to R, or is also equal to M minus R, where R is the rank. So the dimension of the column space of A is equal to R. So we may regard A as a linear map from R of A transpose to R of A. As a map between these two spaces. It has full rank and is thus invertible. So here's why this is true. To see this, if U1 through UN, or how about U1 through UR, form a basis for the column space of A transpose, then if V is multiplied by a transpose of a linear combination of these guys, so say alpha 1 U1 plus alpha R UR, and this is equal to 0, then it must be true that V lies in the null space of A. And of course, this is for all alpha I. But if V lies in the null space of A, and it lies inside this space, then it must be 0. So consequently, we find that the kernel of the linear transformation restricted to the column space of A transpose is 0. And that shows that this map is invertible. And that completes the proof of this statement. And so this is kind of cool because regardless of any, matrix we're studying, we can always understand as our matrix as giving us an isomorphism, or an invertible linear map, between a subspace of its domain and a subspace of our codomain. And it tells us exactly what these subspaces should be. Anyways, that is all I have for today. Just so you guys know, homework 5 is posted, and you can view it in the Discord. It will be due on, I believe, next Wednesday. And good luck, and I hope you guys have a nice weekend.